Introduction. It is always considered being a complex undertaking of the humans to explore Mars. It can be regarded as an enterprise that can assure the potential of the human beings to leave Earth and make their way outside into the cosmos. It could be a small step when taken on the cosmic scale. However, it could result in a significant step for the humans, as it will require leaving the Earth with minimal return possibility. The commitment of this mission is to take several years away from the Earth. With this, there is a very narrow window through which the return is possible. This could be considered to be the major point of difference between the human Mars exploration and the previous lunar explorations. The architecture of the Mars mission has been developed on the works of the Zubrans 1991 and the Synthesis Group 1991. The personnel of the NASA has formulated a reference Mars mission that aims to address the exploration of Mars by the humans. The main principle of the reference mission is to form the base for the comparison of different approaches to select the most suitable one. The reference Mars mission aims to strive for better technical assistance, fewer risks, and lower overall costs than the previous approaches. However, there is still scope for improvement in several areas. These improvements are aimed to achieve the feasible piloted Mars mission. The reference Mars mission can be used for deriving development plans and technology research, defining and prioritizing the requirements needed for the robotic missions to Mars, defining and prioritizing the flight experiments for the human missions to the Mars. These might include the involvement of the Space Shuttle, the International Space Station, or the Mir. Understanding the requirements for the exploration of the humans to Mars. This can be considered in the context of various other space missions along with research and development programs. Having open discussion with the international partners. This could be aimed at the identification of the interests of the potential participants in various specialized aspects of the Mars mission. Providing educational materials to all possible levels for the explanation of various aspects of the interplanetary human exploration. Describing to the media and the public about the feasible and long-term visions of the human exploration of the Mars. Establishment of an end-to-end mission that can be based on the other proposals for effective comparison. The main aim of the Mars mission is to accelerate the stimulation of the development of various alternative approaches that can prove to be effective and can help in the reduction of the potential risks and overall costs. The improvements can be achieved on various levels like mission, the architecture, or the system levels. Architectural level. This level is concerned with the assembly of all the elements that can be integrated into a single unit. The major features of the architectural level that need to be addressed in the Mars mission can be related to the simplification and integration of the overall system. Simplification of the system that can be achieved by the reduction of the system can lower the overall costs and even the technical risks of the system. In the same manner, the integration of the opportunities can link the Mars mission to the development programs and could lead to the sharing of the overall development costs. Mission level. At this level, it could be possible to achieve the reduction in the number of separate launches from the Earth. This would be required for the implementation of the Mars mission and could potentially reduce the amount of risk as well as the overall cost. The simplification of the Mars mission and the improvement of technology can help in lowering the power requirements at the mission level. System level. At this level, the individual performances of the systems as well as the subsystems can be enhanced through proper research and development programs. The technical risks might be reduced through the demonstrations of the ground, the planet's surface, or even the orbit of the Earth. Chapter 1. Mars Exploration Study Project. The Mars Exploration Study Project was undertaken for the establishment of the vision for the human exploration of the Mars. This exploration could serve as the medium for getting an insight of the technical as well as the programmatic requirements that could be placed on the planned as well as the existing agency programs. There have been several workshops held with respect to the Mars mission that has helped in the identification of the major elements of the Mars exploration program. These are: human evolution. Beyond the limits of the Earth and Moon, Mars is the most accessible planet wherein the possibility of sustainable human presence has been believed to exist. The technical aspect of the exploration of Mars must aim at an understanding of what could be the requirement for the sustainability of the permanent human presence beyond Earth. Comparative planetology. The scientific objectives of the exploration of the Mars should be aimed at understanding the planet and its history. In return, it will help in gaining better insight into the Earth as well. International cooperation. The international environment is likely towards putting in efforts towards international cooperation that might be required for a sustained and balanced Mars program. Technology advancement. The exploration of Mars by the humans is currently on the edge of achievability. Therefore, to completely achieve the same, it calls for proper contribution towards the advances in technology. Inspiration. The goals and objectives for the exploration of the Mars are quite grand. They are aimed at motivating the youth and benefiting the technical education to inspire the people of the world. Objectives of the Mars mission. Reflecting on the advancements in the recent technology towards making the Mars mission a success, the main objectives of this mission can be summarized as: establishment of the human missions to Mars and verifying that humans can effectively inhabit Mars. Implement the applied scientific research to use Mars and its resources for the augmentation of the life-sustaining systems. Adopting the methods of basic scientific research for gaining new knowledge about the origin and history of the solar system. The Mars mission is aimed at the accomplishment of the research and exploration activities and also for the safe transportation, maintenance on the surface of Mars and healthy returning of the crew to the Earth. The visualization of the surface exploration of Mars can be given equal priority for the implementation of the applied science research and the basic science research. These detailed objectives of the Mars mission form the basis for providing the definition of the required elements and the operations in the Mars mission. There are several commonly accepted beliefs pertaining to the Mars mission that is associated with the additional objectives, like challenging the notion that the Mars exploration by the humans is an approximate 30-year program that might cost hundreds of millions of dollars. The nations of the world can afford such massive expenditures. However, it is assumed that the smaller the cost, the more easily it gets adopted. Challenging the traditional obstacles related to technical features that could be associated with the human exploration of the Mars. Identification of the relevant technology along with its development and investment opportunities that can benefit both the Mars mission as well as the endeavors that are based on the Earth. Ground rules and assumptions. A number of ground rules and assumptions are required for the purpose of the translation of the objectives of the Mars mission to the positive results. Some of the general rules and assumptions include balancing of technical mission, programmatic and even the safety risks. Provision of a simple operative mission with an approach to emphasize the judicious use of the common systems. Provision of the flexible implementation of the strategy. Limiting the length of time for which the crew is exposed to the interplanetary space environment. Defining the robust planetary surface for the exploration capability for supporting the crew on the surface of the Mars to at least 500 to 600 days on the mission. Defining the capability to live off the land. Relying on the advancements made in the automation for performing a significant amount of routine activities throughout the Mars mission. ensuring that the management techniques are available and can be designed into an implementation program that can help in the reduction of the overall costs. Designing of the proper space transportation system that can be flown in any condition and can offer increased payload delivery capacity. Chapter 2. Mission and Systems. The traditional studies with respect to the human exploration of Mars had focused on the flight and spacecraft. It did not focus on what was the responsibility of the crew once it reached the surface of Mars. The Mars mission takes the aspect of the surface exploration of the Mars that forms the key to the mission. This is applicable for both science as well as for the evaluation of the potential for settlement on Mars. As a result of this, the architecture of the Mars mission allows for the establishment of the robust surface capability with major performance margins. The crew would explore the vicinity of the surface to a few hundred kilometers. They will be able to study the materials present on the surface and will be able to do the modification of the exploration plan for taking advantage of the discoveries. In addition to these, the development of the key technologies will take place that will help in the determination of the settlement issues that might impose a great amount of workload on the crew of the Mars exploration. For improving the effectiveness of the operations at the surface of Mars, the supporting systems must be made highly reliable, responsive and autonomous to the needs of the crew. Some of the needs might not be anticipated during the preparation and training of the crew. This could challenge the overall operation system and the management in a significant manner to support the crew under new situations. Mission Design. Under the design of the Mars mission, the selected crew will have the responsibility to travel to and from the surface of the Mars on faster transit, like 4 to 6 months, and to spend longer periods of time, usually 18 to 20 months, on the surface of the planet. This is contrary to the alternative approach that would require longer time in space and reduce time on the surface. A typical trajectory for Mission Mars has been designed in the worst-case mission case to handle the worst situations as well. The transit legs have been designed in less than 180 days in both the directions. For better opportunities for Mars mission, the transit legs are designed on the order of 130 days. Shorter transit times would reduce the time spent by the crew in the zero-G length of the typical tours of duty to the International Space Station. In addition to this, the faster transits will also help in the reduction of exposure to the galactic cosmic radiation and also the probability of encountering any solar particle events. By the reduction of the exposure to zero gravity and radiation events, it could help in the reduction of the potential risks to the crew. The strategy that is chosen for the Mars mission is referred to as the split mission. This helps in breaking the mission elements into several pieces that can be launched directly from the surface of the Earth with the help of various space launch vehicles. The strategy then aims to assemble these pieces on the surface of Mars that will require both landing and the mobility of the major elements on the surface, such that they can be allowed to connect to be moved into the close proximity. Another major determinant to the strategy of the split mission is that it can also allow the transportation of the cargo to Mars without any crew during the launch opportunity that is held prior to the crew departure. This allows for the transfer of cargo of lower energy and longer transit time trajectories. This also allows for the crew to be sent on a higher energy requirement and shorter time trajectory. As the Mars mission is broken into separate launch windows, this will allow the infrastructure to be checked before the commitment of the crew to the mission. This will also allow for the robust capability with the possibility of several duplicate launches on subsequent missions that would act as backup for the earlier launches or for the growth of the initial capability. As per the mission sequence that has been analyzed for the Mars mission, there will be subsequent launches from Earth to Mars. The initial launches would not contain the crew involvement. However, these launches would carry the infrastructure and various necessary elements that would be required on the surface of Mars for future use. Each of the remaining opportunities that will be analyzed for the Mars mission will send one crew and as many as 2 cargo missions to the surface of Mars. These cargo missions will consist of an ERV, Earth Return Vehicle, on one flight, as well as a lander that would carry the MAV, Mars Ascent Vehicle, in addition to the extra supplies. This sequence would gradually build up the assets on the Martian surface such that by the end of the tour of duty of the third crew, the basic infrastructure on the surface of Mars is able to support the permanent presence on the planet. During the first launch opportunity, as many as 3 cargo missions are sent on minimum energy trajectories directly to Mars. Launch 1 would deliver a fully fueled ERV to the orbit of Mars. Launch 2 would deliver an unfueled MAV, a propellant production module, liquid hydrogen to be used as a reactant for the production of the ascent vehicle propellant, a nuclear power plant, and as much as 40 tons of additional payload to the Martian surface. After the descent stage has landed on the surface of Mars, the nuclear reactor deploys itself automatically on an average of several hundreds of meters from the ascent vehicle. The Mars atmosphere is then used as the feedstock. Using the same, the propellant production module starts the manufacturing of around 30 tons of oxygen and methane that will be required for the delivery of the crew to the Mars orbit. The production of the same is completed in almost 1 year, particularly several months before the scheduled departure of the crew from the Earth. The third launch would land in the vicinity of the first descent vehicle, and it is used for the delivery of the surface habitat or laboratory. It would also help in the delivering the non-perishable consumables for safe living and also a second nuclear power plant to the surface of the Mars. The second nuclear power plant would deploy itself automatically near the first power plant. Each of the nuclear power plants is capable of providing sufficient power of around 1600 kWe and therefore offers complete redundancy with the power production function. During the second launch opportunity, 2 additional cargo missions and the first crew to the surface of Mars are launched. All the assets that have been previously transported to Mars have been now cross-checked. MAV that is already present on the Martian surface is verified to be fully fueled before either the additional cargo missions or the crew is launched from the Earth. The first cargo launch of the second opportunity is the duplicate version of the first launch from the first opportunity. This would deliver a second fully fueled ERV to the orbit of Mars. The second cargo launch also mirrors the launch 2 of the previous opportunity. This is aimed at delivering the second unfueled ascent vehicle and also propellant production module. These systems are aimed at the provision of backup or even in the extension of the capabilities that have been deployed previously. For instance, the second MAV and the second ERV are available for providing the first crew with redundant means to each leg of the return trip. If in any case either the first ascent vehicle or the first return vehicle becomes unoperational after the crew has departed from the Earth, then this crew can make use of either of the systems that have been launched in the second opportunity. If the first ascent and return vehicles operate as required, then the systems will deliver the support to the second crew that will be launched to Mars in the third opportunity. In the second opportunity, the first crew departs from Mars from the Earth. They leave Earth after 2 cargo missions have already been launched. As they are sent on a faster trajectory of just 1800 days, they might arrive on the surface of Mars as many as 2 months before the cargo missions. The crew that lands on the surface of the Mars adjust themselves in a substantial manner in the identical habitat that had been previously deployed on the Martian surface. After the crew has entered the highly elliptic orbit of the Mars, the crew descends on the transit habitat to explore the surface with the other elements on the surface outpost. The exploration of the surface by the humans and the robotic vehicles can include a wide range of activities, including observing and performing the analysis of the surface and the subsurface geology, observing and performing the analysis of the composition and the structure of the atmosphere, collection of the samples and then examining them in the laboratory present on the surface outpost, performing various experiments that are designed to gauge the ability of humans to inhabit the surface of Mars. Before the arrival of the first crew on the surface of Mars, TROVs, telerobotic rovers, are also delivered to the Martian surface. These rovers are designed in the manner such that they perform intelligently for the achievement of various objectives without any assistance by the humans. When the crew arrives on the surface of the Mars, the TROVs are available for doing the teleoperation by the crew. The TROVs are also designed for providing global access and might even return samples to the outpost on the surface of Mars, even from hundreds of kilometers from the site. This can be achieved if they are deployed as many as 2 years before the arrival of the crew on the surface of Mars. The outpost laboratory on the surface of Mars is fitted for the provision of mineralogical and the chemical analysis of soil, rocks, and even atmospheric samples. They also make it possible for the undertaking of various kinds of geochronologic analysis on the surface of Mars. The main purpose of these studies is to provide support to the field investigations, answering the sharper questions and allowing the human explorers to narrow their focus on the sites of optimum sample collection. As per the hypothesis, the crew would be able to return the sample sites and enable the gathering of the specific samples to test the hypothesis. In the end, the selected samples will be returned to the Earth for better and detailed analysis. As per the experience, the extent of the human exploration will expand from the local to regional scope. Regional explorations that might last for around 2 weeks will make use of the mobile facilities. These too might be conducted at certain intervals in a few months. Between these explorations, the research and analysis in the laboratories will continue to take place. The crew is also supposed to spend a considerable amount of time in performing the maintenance and also the housekeeping tasks. The deployment of the support capability for bioregenerative life on Mars can be the earliest form of activity once the crew has landed on the Martian surface. This system is, however, not required to maintain the health and energy level of the crew. Still, it might help in improving the robustness of the life support system and can serve vital to the achievement of the early objectives at the surface outpost. The activities of the crew that is related to the life on another planet are viewed as substantial experiments. There are minor modifications made in the software and hardware that can result in the ordinary experiences to be used as a medium to provide the objective databases. This might help in the proper understanding of the requirements for the scope of human settlement on Mars. After the stay of the first crew on Mars, each crew would make use of the ascent vehicles that had previously landed or the in-situ resource utilization fueled ascent vehicles where they will encounter the ERV that has been waiting for them. The crew will then return to the Earth in the similar habitat that has been used for the outbound transit leg. This habitat is the part of the ERV that has been deployed in the previous opportunity. Chapter 3. In-situ resource production. The production of the propellant from the Martian resources is carried out in a highly automated system. This can be considered to be another determining attribute in the Mars mission. The technology that has been used in the production of methane and liquid oxygen from the atmosphere of the Mars or the hydrogen feedstock from the Earth can be used for the enhancement of the performance. This can also appear to be feasible in the technological applications in the upcoming years. With the help of the split mission, it has allowed the production of the propellant that can be checked out and operated for the production of the required propellant before the launch of the crew from the Earth. In addition, the propulsion of the spacecraft, the production capability of propellants on Mars, can also provide for reactants for fuel cells, surface transportation, and providing backup of consumable items like nitrogen, argon, and oxygen that might be vital for the life support system. Flight crew. In the mission to Mars, the human beings are the most important assets. Therefore, the humans must not become the weak link. The main objective of the human beings to spend as many as 600 days on the Martian environment is to provide the supporting system to the overall Mars mission. Once the crew has committed to the Mars mission, it must be prepared for the completion of the full mission without any further resupply from the Earth. There cannot be provisions of unlimited resources within the budget constraints and the performance of the mission. The resources of the crew will be either with them or will be already delivered to Mars before their mission. Therefore, the trade-offs must be made between the comfort and cost as well as in the risk and performance. The self-sufficiency of the crew is required and vital for the long duration of the mission. The fact that their distance from the Earth is great, it makes it quite impossible for the traditional levels of communication and support by the controllers present on the Earth. The crews would need their own skills and the presence of specialized support systems and training to meet the new challenges of the mission. The nominal size of the crew for the Mars mission is considered to be around 6. This fixed number for the crews is considered to be reasonable from the point of view of the traditional studies and the experience from the starting point of the study. Therefore, considerable efforts would be required for the determination of the absolute requirements of the crew size and composition. With the help of this determination, there have to be considerations made for the tasks required of the crew, risk and safety considerations. It will also include the consideration of the dynamics of an international crew. The crew members would be selected on the basis of their ability such that they can relay their experiences back to the Earth in an interesting manner. They should also be given enough free time for the appreciation of the experience and for providing the opportunity to be the first human explorers on Mars. There will be a requirement of significant crew training that can ensure that the crew is productive enough throughout the Mars mission. Robotic precursors. The missions of the robotic precursors will play a major role in the different areas of the Mars mission. The first area is for gathering of information about Mars that can be used for the determination what specific crew activities should be performed and the areas where they will be performed. The next area helps in the demonstration of the operation of the key technologies that might be required for the Mars mission. The third area is for the purpose of landing, deployment, operation and maintenance of the significant portion of the surface systems that might be prior to the arrival of the crew on Mars. For the optimum performance of the Mars mission, it will be necessary for the picking up of the landing site based on the ability for the achievement of the objectives of the Mars mission. In addition to this, the site must also be consistent with the operational considerations like the surface operational safety and the landing. Detailed and descriptive maps of the candidate landing sites are built from the data that is gathered by the precursor mission that will define the safety and the operational hazards of the sites, as well as the confirmation of getting the access to the scientifically interesting locations that could be possible for the humans and the robotic vehicles. The robotic surface missions, that might include the missions for returning samples, could be required for the confirmation of the remotely sensed data from the orbits and also for the satisfaction of the protection issues of the planets. For the satisfaction of the objectives of the human habitation, it could be considered highly desirable for the location of the outpost site where water can be readily extracted from the minerals or from the ice deposits present on the subsurfaces. For the accomplishment of the Mars mission, there is the need for certain advancements in the critical technologies. The missions of the robotic precursors will offer an opportunity for the demonstration of the technologies that can help in the addition of immeasurable confidence that might be needed for the human Mars mission. The first phase of the human exploration of Mars is characterized by the automated landing of the elements of the surface infrastructure that would include the system for the production of the propellant and the life support consumables, including the 2 habitats, surface transportation elements, and the power systems. All of these systems will be set up and delivered and can be checked out with the help of the robotic systems that are supervised and operated from the Earth. The propellant that is required for the MAV can be stored and produced, as will the water and oxygen caches for the habitat. The overall site will be prepared for the receipt of the second habitat. Chapter 4. Launch Systems. The scale of the ETO, Earth to Orbit, launch capability is determined by the weight of the largest payload that is intended for the Martian surface. The nominal design for the individual packages that have to be landed on the surface of Mars in the Mars mission is expected to be around 50 tons for the crew habitat of 6 members that is transferred on the high-energy orbit of Mars. This requires the capability of a single vehicle launch that would range from 200 to 225 tons. As the development of the 20-ton of the vehicle's raise would lead to cost issues, the option of launching the pieces with the help of smaller vehicles and their assembling into the space prior to the launching of the vehicles could be considered. This smaller launch of the vehicle can have the advantage over moderate costing and the capability of the Russian Energia program. However, the launch of the smaller vehicles could pose several other issues as well. The simplest implementation of the small launch vehicle is for the docking of the elements in the Earth orbit. This would result in immediate departure to Mars. To avoid the loss of the cryogenic propellants in the various stages of the departure, all the elements must be launched from the Earth in quick succession. This would place the strain on a single launch facility and the ground operations crews, or would require the close coordination of the several launch facilities. Assembling of the Mars vehicles in the orbit of Mars and then their loading with the required propellants from the depot of the orbit just before their departure might evade the strain on the launch facilities. Therefore, the permanent construction or the facility for propellant storage in a single orbit of the Earth cannot be considered to be an optimal solution. The choice of the launch vehicle for the Mars mission would remain a significant issue. Mars Mission and Systems Summary. To summarize the Mars mission, the major distinguishing characteristics of the Mars mission would include no extended LEO operations, fueling or assembly, no involvement of the Mars orbit prior to landing, shortened crew transit times to and from Mars that could be less than 180 days, longer surface stays times from 500 to 600 days for the first as well as for the subsequent crews who will be exploring Mars. A heavy launch vehicle that would be capable of transporting the crew or the required cargo directly to Mars. The vehicles that are capable of delivering needed launches for a payload of the first human mission to Mars and the subsequent launches as well. Exploitation of the indigenous resources from the beginning of the program with vital benefits on the concept of performance and in the reduction of the risks involved with the Mars mission. Availability of the option Aboard to Mars strategies for a surface that would be based on the robustness of the capabilities of the Mars surface and the overall cost of the trajectory aborts. Common surface or transit habitat design. The main tenets of the safe and robust environment for the crew throughout their exploration of the Martian surface. Substantial autonomy of the system operations and the crew from the ground control itself. Conclusion. Based on the Mars mission and the programmatic points of view, several points of conclusions and recommendations have been made in the significant areas like Mars mission, technological development, overall system, environmental protection, cost of the overall program, participation of the international bodies, and the proper organization and management of the entire program. A feasible mission scenario and the suite of vehicles along with the other systems must be integrated in a proper manner for meeting the objectives that have been initially set out for the study. In addition to this, the Mars mission would also address the long-standing issue that is with regard to the flights of the extended duration and the safety of the crew. These must be adopted with a view that the surface of the Mars can be considered to be a safe haven and that the procedures and the equipment should be developed by keeping these factors in mind. The Mars mission would include the assumptions based on the technological advancements for the future development, and that would contribute to an estimated cost of development that can be presumed to be higher than the currently supported system. Both the cost and the technology factors must be addressed in a proper manner, and the alternative systems and missions could result in the better program for the exploration of Mars by the human beings. However, the systems and the missions that have been described here can reduce the overall cost of the program in a substantial manner. At the same time, it could also present a more robust and better approach than the previous topics of study in the concerned field. Various recommendations that have been proposed by the Mars mission include use of the study as an informal baseline against the alternatives that would be present in the future times should be compared on proper grounds. To continue the alternatives based on the investigation of the mission scenarios and the systems for the improvement of the Mars mission. This also calls for the suggestion of a better alternative to improve the overall Mars mission.